It's, I did find a volume thing that worked. Just to show you how that works. They've got the x-axis and the y-axis. You see that they have a curve that's bounded. What's the curve? Hold on. Well, they don't tell you what the curve is, but anyways, you've got this curve here that kind of acts as an upper bound. Let me kind of get rid of it. You see these two curves here?
Yeah.
So they're going to make cross-sectional areas that are perpendicular to the x-axis, the bottom here.
The green line, the green axis is the y, and then the red axis is the blue.
Okay, the x-axis we'll call this is x, this is y here.
Yeah.
So this is your 2D. See, they're making cross-sectionals this way, so they're perpendicular to the x-axis.
Yeah. Call it old red bull.
And then the z is the blue is the z, and we're going to go up out of the paper. All right. So if I do semicircles, like here, you can see the cross-sectional. See how this is the length between y. You just subtract the areas, right?
Yes.
That's your length, and they drew a semicircle out of it. So here I've got two, and you see the more I add, I get this thing that looks like that. Okay, so nice, pretty volume. Okay, I can find the volume of that by basically integrating the areas of the semicircles.
So
now,
to find the height of the blue, you subtract
top minus bottom. We'll get there. Okay, I just wanted you to see a picture of it. Here's an equilateral triangle, so you can see it changes depending on what the cross sections are. Here we made triangles out of them. Okay, and it looks like that. And that pretty. Oh, you can drag this around. I'm pretty sure too. Look at that. Yeah. Okay.
Feels like a fish.
Yeah. Oh, it moves. Wow. Okay. I don't know how exactly I did that, but okay.
Looks like the New York thing.
And then I turned them into squares. There's some squares. All right. And you can see that, yeah, you can do anything you want. You can do circles. They don't have circles as an option, but.
It is both squares and triangles.
Oh, yeah. Well, there's just squares. Let's just do squares. Okay. So you can see it makes some pretty funky things, and you get the volume of these just by integrating the cross sectionals.
Drag it all the way to the right.
Drag what all the way right?
The end bar.
This?
It's just
Yeah,
pretty
go
much the
for it.
whole space.
It just fills it in and makes it a solid now, right?
That's so cool.
Okay. So I found one that worked, so yay. I also have a where's Wolfram? I might as well show you this one. This one does kind of the same thing. It's something I downloaded. See, like here's a, looks like a sine and a cosine curve.
Yeah.
So if the cross-sectional areas, let's see, what did I make them? I made them squares, so if I drag this around, you can see that I'm finding the volume of this funky thing. Okay. And you could do equilateral triangles. Now you can see they're triangles.
That's cool.
Ooh.
Okay. Your semicircles.
Oh, that's really cool. I like that.
It looks
And-
like a base.
Yeah, there's a rectangles. All right, so we can get some volume of some pretty funky things. I wanted to show you that. All right, so now we're going to do it. I wanted to go back and fix my isosceles triangle. When you have the diagonal on the bottom, so basically you need to know these areas because they give you like these as bases. All right. You want to know that they're calling this S with this formula. All right. So the reason that this is true is for an isosceles triangle, these are both the same, right?
Yes.
All right, so, and I know that this is 45, this is 45, and this is 90, right? Isosceles right triangle. So the area of a triangle, like if I split this, this is half of this is half of the diagonal, right? This is an isosceles, so this is also half, this is reached 45, and this is 90, right? So the area of this is 1/2 base times height, so it's 1/2, I still do, oh no, the base would be the S, the whole length.
Yes.
And the height is S over 2, so you get S over 4, or S squared over 4. Okay? My point is keep this list handy. I think it gave you any one of these. All right, on the AP test, any one of them. All right. So let's do some. Oh, there's trapezoids too. Triangle, trapezoid. All right. So I would suggest drawing a picture so that you know what it is. You don't have to draw a 3D picture, but you need a 2D one. All right. It says let the base of a solid be the first quadrant plane. In the first quadrant, bounded by y equals 1 minus x squared over 4, and the x-axis and the y-axis. So that's 1 minus x squared over 4 is a parabola.
Yep.
And the height would be 1 0 and x is 2. Is that right? I did in my head.
Yeah.
Okay. So it's going to look something like this. You can graph it on your calculator. Most of these are calculator problems anyways. So I'm looking at this. Okay. Okay, so suppose the cross section's perpendicular to the x-axis or squares. Okay. So if they're perpendicular to the x-axis, we're slicing this way. That's what's important, right? That means I'm doing an integral with respect to x. I don't have to be able to draw this. I mean, you can visualize squares going back behind this, maybe. Make a whole bunch of squares. So all I need to do is add up the areas of squares, right? So the side of the squares is how much? How much is this length right here?
1
It's 1 at the beginning. How much is it as I go down the curve? Well, how high is this?
3/4.
No, I wanted to.
Oh, I thought it was at 1. My bad.
Right? What's the height of this? That's y, right? That's 1 minus x squared over 4.
Yes.
So each of those rectangles have a height of 1 minus x squared over 4.
Yes.
So the area of the square, so the length of the side is 1 minus x squared over 4. Yes?
Okay.
So the area of the square is side squared, so you're just going to integrate side squared. So it's 1 minus x squared over 4 squared, right? And then you have limits.
Yeah.
Right? So it starts at 0, x starts at 0, and we decided if you want to figure out where it ends at, if you didn't know, set it to 0. So I get 1 equals x squared over 4.
4 equals x squared.
Yeah.
X equals 2.
Yeah, so x is 2. Negative 2 is, I just said the first quadrant, so I ignored this part right over on the left. So if I do this integral, I'm going to go from 0 to 2. I'm going to use my calculator for these, math 9. All right, unless they tell me otherwise, I just use my calculator and get the answer. And that's the volume of the solid. Okay. So I'm just going to plug it in math 9 real quick. Okay. Math 9. I'm going to go from 0 to 2. 1 minus x squared over 4. The only thing with this, I will tell you, be careful on the calculator, you type it correctly. It's easy to type wrong.
1.06.
I don't know, I've done it yet. I get 1.0667, whatever, okay? These 3 decimal places, okay? So that's the volume.
Yes.
Okay, so the idea is you integrate the cross-sectional area, whatever it is. If it's perpendicular to the x-axis, if you bring it vertically, you do it with respect to x. If you do it horizontally, you do it with respect to y. Okay?
So if it was the other way, what would change about this?
A lot would change. All right, if I go it the other way, oh sure, why not? Let's do it the other way. I wasn't planning on doing it really, but sure. I need a different color.
Got it.
Red. Let's see. Yeah, red one. All right. So if I slice this way, right, the height of the squares is now x, right? So I need to solve this equation for x. All right. So let's see. What was it? Y equals 1 minus what was it? X squared over 4. So if I multiply by 4, I get 4y equals 4 minus x squared. So x squared equals 4 minus 4y. Take the square root, so I get x equals plus or minus the square root of 4 minus 4y. Now, positive or negative square root, what piece am I picking? That's going to be the positive piece, right? Because it's above the x-axis.
Yeah.
Okay. So basically for my integral now, the length of the cross-sectional dealie is square root of 4 minus 4y. And so I'm going to take the side and square it, but I have to integrate with respect to y. Y here starts at 0, and how high does it go? 1, right? So if you plug that in the calculator, you should get the same answer. No, sorry, you will not get the same answer. Is it the same solid or is it different? That makes the same solid. You should get the same answer. It's rare to get the same answer, but that makes the same solid in our case, I believe. You get the same answer? That doesn't happen. I mean, just because it makes the same solid. I think it does.
Wouldn't it Those, it'd be 2.
Huh?
I got 2.
You got two?
But
I
what if
got
the
two
square
too,
and
so it's
square
I guess it's slightly different.
root- What if the 2 and the 2, or the square and the square root cancel?
Yeah, they do. You can get rid of them.
Yeah, so it could be two,
It's 4 minus 4y, right?
1 minus y.
What are you talking about?
2 times 1, or 2 times the square root of 1 minus y is what you could do with that. If you wanted to.
Yeah, if you want to. Yeah. You don't need this for yeah. Okay. We're just doing on calculator, so I want to simplify it now. Okay.
Then you can pull it out of the integral.
Yeah, I could do a lot of things. Okay. All right, I get you on. I wasn't trying to go there right yet.
Yeah.
All right, so the base of the solid, the region between one branch of sine x and the x-axis. So I'm going to draw you a picture of sine x and the x-axis. So that would be like this hump right here.
Yep.
Right? And where does sine x end here?
Pi over 2.
It's not pi over 2. Pi, right? The sine of pi is 0. Okay, so we're talking about this. All right.
So this-
Let's read the rest of the question. Each cross section perpendicular to the x-axis is an equilateral triangle sitting on, it's supposed to be its base, on the xy plane. Alright, so it's sitting on its base, which means this is the situation. There's no way I'm going to draw this well.
Oh,
We're making equilateral triangles, right? So what I need, sorry, no, that's bad. Can I get rid of this? Let me draw it. That's not good. Alright, pi. Alright, this is the length of the base. So if this is the base of the equilateral, you've got like triangles popping up out of there. Alright, Miss Miller's not good at drawing. Okay, so we got all these triangles, okay? Now, what's the length of the base of the triangle? Or the side?
why?
Y, right? Y is sine x. So the side of the triangle equals sine x. Yes? So what's the area of an equilateral triangle? You have a list in front of you, and that's why I want you to know it.
Root 3 over 4
Yeah, so we have to integrate root 3 over 4 times sine squared, where the side is the sine. So it's root 3 over 4. Sine squared of x, as x goes from what to what? Where does it start here?
0.
0, and it ends at
Pi.
pi. And you can plug it in your calculator. I'm going to save me some time and not do it. Okay? You can plug it in your calculator.
Oh, we're recording still?
Yes.
Okay.
I turned it off during lunch. Okay, are we okay? Okay. So the whole idea is you find if you're perpendicular to the x-axis, you got to find the length and you plug it into the appropriate area formula. Okay. Do it with respect to x. If you're perpendicular to y, do it with respect to y.
This one would be different though if you did it.
Oh yeah, it would be totally different, right? If I did it with respect to y. You guys see that? Yeah. Okay, because you get a really long triangle out here, right? At the x-axis. They're not the same usually. That's kind of a surprise. I don't know if they were.
The video's gonna be on your website.
Huh?
The videos.
Yeah, I'll put them up there.
Oh, okay. And like for squares, they would always be the same though.
Okay, so let's try one. Another one. It says the base of the base is the region in the xy plane bounded by x equals 4 minus y squared. Do you know what that looks like? Hopefully, it's a parabola. It's kind of sideways though because it's x equals y squared. So the most it could be when y is 0, x is 4. Because y is negative, it's going backwards, right?
Yes.
Okay.
And I can label some other points. When y is 2, x is 0, so I know that that's 2. And that's 2, right? Alright, just labeling some points. Alright, you have to, I'm going to tell you to draw a sketch, because sometimes the area it's bounded by isn't what you think it is, alright? So you want to kind of shade what they're saying. And x equals 0. So x equals 0 is what kind of line? Vertical. Alright, so the area, we're talking about this right here, right?
Yes.
Okay. Find the volume if the cross sections perpendicular to the x-axis are. So what I'm going to do is first of all figure out what this distance is, and then I just plug it into the appropriate area formula, right? So what's on top? So first of all, first question, do I be doing this with respect to x or y? X. So that means I need to solve for y, right? All right.
Where are we going?
I have to find this length right here. That's this is the length of my cross section.
2?
It's not 2, it's varying, right? So let's solve this for y. So I have y squared equals 4 minus x, is that right?
Yeah.
So y equals plus or minus square root 4 minus x. Why did I get plus or minus?
Okay, it's on bottom.
Yeah, you got, so this is the positive curve right here. It's root 4 minus x.
Oh.
And this is the negative curve, right? Is that right? So the distance between them is I take top minus bottom, right? So the length of that side would be root 4 minus x minus negative root 4 minus x. So in other words, twice
Yeah.
root 4 minus x.
Which
So
makes
that-
sense.
Yeah,
because-
they're both the same, right? Makes perfect sense, okay? So now that I've got the cross-sectional, the length of the side, I just plug it into the formula, all right? I'm gonna skip semicircles because semicircles, a little bit of an issue we'll talk about in a minute. Yeah, let's skip semicircles. How about rectangles? Let's do that first, all right? So what's the base of the rectangle? This is the base, right? What's the area of a rectangle? Base times height. So the base is 2 times root 4 minus x.
Yes.
And what's the height if it's half the base? Root 4 minus x, right?
Wouldn't 3 times that?
What?
No, could you not do that?
No, it's 2 times 4 minus x. You multiply the square root, right? Okay. So if you want to get rid of the square root, you can. And then I just got to get my limits. So where do I start and where do I end? Where does x go from what to what? Where does it start? Look at the picture.
Wouldn't the height be the same from 0?
No, the height is half of the base, so I just divided this by 2.
Yeah.
Okay, so it starts at 0 and it goes to what? 4. Right. And just do that on your calculator. All right, I'm happy if you get the intervals because that's the challenge. Okay. Let's do an isosceles right triangle.
So hard to visually.
With its leg on the base of the solid in the xy plane. So this is the leg of a triangle, right? Yes? So the area of an isosceles triangle, let me go back to my formulas, with its leg on the side. Right there, s squared over 2. Okay? Okay, so I'm going to do the integral from 0 to 4. What's the side? The length of the side is still the same, right? It's 2 times root 4 minus x. Yeah. So it's 2 times root 4 minus x. The length of the side squared over 2, right? And I just plug that in the calculator.
What?
Here, this came up here. This should be with this. Okay, so it's side squared over 2. Right? This is our side. No matter what, this is our side.
Yeah.
Okay? So let's go to semicircles with diameters on the base. All right, what's the area of the semicircle? 1/2 r squared. All right, so now I'm going to draw something else over here so you can see it. Imagine I've got semicircles. So this is the diameter.
No, you have to divide by 2.
Yes, you do. Okay, you see what he's saying? The length of the curve here, 2 root 4 minus x, is the diameter. So if I want the radius, I have to divide it by 2. That's the catch with semicircles.
So you can just use 4 minus x.
Yeah. So the radius is half the diameter. So it's 1/2 times 2 root 4 minus x. So it's just root 4 minus x. All right. So I'm going to integrate again from 0 to 4 of 1/2 pi r squared. R is, if I square that, can I just write 4 minus x? Is that all right?
Mm-hmm.
Yep.
I just do that integral on my calculator. Okay. So the little catch with semicircles you have to be aware of. Okay. Now I have it a little different. Semicircles with radius is on the base. So what's changed? So I'm not going to be able to draw this. I doubt it. Okay, so I have a semicircle. This is a radius, so we're going to go down, down. Right, we have bigger semicircles, right? Okay.
Oh God, this is. Ugh.
Okay. You're just, well, what's the radius of the semicircle?
I know, it's just so hard to like,
It's hard to visualize, yeah.
yeah,
Okay, so what's the radius?
the diameter.
The base, right? So it's, I don't divide by 2 in that case, right? So we're gonna go, I'm gonna go from 0 to 4, 1/2 pi. The radius now is still 2 times root 4 minus x squared, okay? But you see how all I'm doing is once I have the length of the side, I'm just plugging it into the appropriate formula for area. And I gave you a list, yeah, you need to know because I can give you any one of them. Okay?
This ain't hard.
No.
Why is it 2 pi?
Why is it 2 pi? No, it's not.
Why
It's
is
1
it
half.
2 pi?
Sorry, it's my writing. Is that better? 1/2 pi r squared. Okay, semicircle.
Wait, what?
Huh?
What did you do the boxes for?
Because he thought I had a 2, my 1 got ate up by my 4. It's my writing.
Oh, okay, yeah.
Okay, I was trying to fix it. All right? Okay. So all you're doing is integrating the cross-sectional areas. All right, so now we're going to go the other way. Find the volume of a solid whose base is bounded by the graphs of y equals x cubed. So I'm going to draw this. It's very important to draw because you got to pick the right region. Y equals 0 is a flat line, and x equals 1. So we're talking about this area right here, but we're not. Yes, I am. Okay. Sorry. Yes, I am. Okay. Now, be very, very careful with this. Y equals 0. Did I do that right? Yeah. Okay. And so this is the curve. I'm going to do it with respect to y, so I know that x is the cube root of y. Is that right? Mm-hmm. Okay. So on perpendicular y-axis, this is the length of the side. This is where you're going to have a little hole in the solid. All right, it doesn't go down the y-axis. So my question to you is, what's the length of the side here? This is why the area was important we did yesterday. Okay, how would you find the area of the section? Right? Yesterday, you do right minus left, right? If you're doing respect to y, so you do the same thing, right? To get the length. So the right here, what's this curve right here? 1. X is 1 minus cube root of y. That's the length of a side. All right? And so I'm going to integrate the side squared, right? Because they're squares. Now the rest is easy. And y goes from 0 to what? Where do these curves intersect to? Huh?
0 to 4.
No,
Or 1.
If x is, if y is x cubed, if x is 1, what's y? 1. 1. So this is the point 1, 1. So the interval goes from 0 to 1. Okay? So if you got some space, you gotta do right minus left or top minus bottom. Okay, we'll continue it on Monday. We have homework 1 and 2. I'll check those both on Monday, okay? Do the homework. You see this takes a little bit of thought. Okay, the intervals are, you know, it's setting up the intervals that it's difficult here.
Hey, Miss Miller, for this unit, could you draw things like that? It'd be a lot better to see them
Things like what?
like that.
I know. I only want to look at the 2 dimension. I actually don't for a reason. Yeah.
I cannot see it otherwise.
Yeah.
2 times the pi.
You don't have to see it. You just got to see the length of the side.
Fair.
2 times the pi.
That'll work.
Was it a flower triangle?
Yeah.
Oh, I'm sorry. I thought it was a square. Ooh. Okay, we fix this.
Oh yeah, equilateral
3 over
triangles.
4. I thought they were squares. Okay, yeah. Got to use the right formula.
Oh, that's actually really interesting. The only difference between a square and an equilateral triangle is that.
Root 3 over 4.
Yeah, that's cool.
Wait, so that's a 4 right there?
Yeah.
Miss Miller,
Yeah.
how long are you staying to?
Huh?
How long are you staying to?
I put it on the chalkboard.
Alright, fucking y.